First of all, this problem, we've already modeled the walking around, so I'm not going to do that very much. How many are there? 9? 9? 9. Okay, what I would like to do is to explain to you how I use this problem in my class. Because the second part of this is not about what to do. The second part of this is about how do you make it happen. So I would like to put the context in. You believe that there's 9. Okay, we'll go with that. This is the first problem my students get 10 minutes into class the first day. The first day of class, you got to hit them with some math. You can't sit there and give them the rules and pass out all this stuff and let them go home not thinking about what they're going to do. You got to hit them with some math right away. Otherwise, well, David Johnson said it best. David said, when my kids go home at school from the first day, at the dinner table, I want them to say to their parents, you can't believe this crazy math teacher I've got. I want them talking about my math class. And that isn't going to happen if you spend 45 minutes going over all the rules. They can pick up the rules as you go along. So this is the problem I give them. Not a very exciting problem, but it doesn't take any explanation or whatever. Now let me tell you about where it goes. Some kids get 7, some kids get 8, some kids get 9, some kids get 27. How do you get 27? You don't know the difference between a square and a rectangle. So you're assuming that this is a square. Well, that's what I was talking about earlier in terms of context. And I want to get to that right away. Why? Because first important lesson for you to learn in my class. The language that we use in this class is really important. The word square means something different in this room than it does out in the world. Right? We're not going to be using square as in the sense of a square dance, or a town square, or a peanut butter square, which is actually a peanut butter parallelepiped. But the word square has a very distinct meaning, and when I use that word square, and when you use that word square, we better mean the same thing. Because the people who got 27 did some good math, maybe. They're thinking, their logic was fine. They got a completely different answer because they weren't doing the same problem. Why? Because we weren't using the words to mean the same thing. So we're going to do some work about making sure that the vocabulary and the notation is clear. When I use the word line in this class, I mean something different than the 50-yard line. When I use the word line segment in Ray, and here's the notation for it, and you know that, I'm not going to do that, but that's the introduction to those particular things. So, now that we've got that cleared away, exactly what is a square? And so now we can spend a little bit of time talking about what a good definition is. And how much you need and what a square is and all of that. And then we come to the best part. How do you know that any of those are squares? Exactly. How do you know? The only right answer to this question is we cannot answer the question, there's not enough information. Because I haven't told you anything about which are right angles and which are congruent segments and any of that. Now the kids have been taught justly so in 3rd grade, 4th grade, 5th grade, to recognize a square. That's important. I don't think they need to be able to write out a word-for-word definition of a square in 2nd grade. And they need to be able to say, that's a rectangle that's not a square. I do believe they need to know that a square is a rectangle as soon as you can get that across, but they need to be able to recognize the shapes and put names with them. They need to know what a rhombus looks like and be able to put a name to it. It makes our work a lot easier. But now, in this course, we want to make sure you understand what things you can assume and cannot assume. And you can never assume measure. You can never assume measure. So unless I tell you that those are right angles, and unless I tell you that those segments are the same length, then the only correct answer to this problem is we don't know. I have had 2 students say that. However, both of them were younger siblings of other students that I'd had in class before. But think about that. Think about that. That means that before they went to class, their brother or sister said, oh, are you going to love that first day with Mr. Benson? He's going to give you this problem, and everybody's going to work on it, and here's what's going to happen. It also means that right up front, I can establish my working procedure. I am going to give you a problem before I show you how to do it. I'm going to ask you to work on a problem, and I'm not going to stand there and show you how to do it and have you do examples. I'm going to give you a problem I think you can work on, and I'm going to try my hardest to make sure you get it wrong. I'm going to give you a problem you think you did right, and then when we talk about it and discuss it, you're going to find out where you went wrong. I will not succeed every day. Sometimes I won't be clever enough to write that problem, and you will outwit me and you will get it right. But you need to know that I hope I will never give you a problem that I think you all know how to do, because that would be wasting your time, and we don't have enough time. Why would I ever give you a problem if I was sure you could do it? I mean, that's just downright stupid. So when you get a problem in front of you, you should know that I think you probably can't do it unless you're really clever and unless you think about it. So I would like to think that my children would all get that subtraction problem right, because they know that what is self-evident at first is probably not the problem that was asked, that the problems are going to go a little bit further. Okay, anyway, so that's the first day of class. And I talk about the 50-yard line and the foul lines and all that. And I get a little excited about it, as I did here. And the kids walk out of there with their mouths open. But they know that this is going to be an exciting, different, interesting class. And I've got them. There will be days when it's not so exciting, when it's not so interesting, but I want to work real hard in all of my classes to make sure that very first problem is one that is memorable, and also that it teaches something. I also want to come back to this because I didn't discuss why did I pick this problem. I just gave you the problem and you worked on it and did exactly what I wanted to. It was a very good problem. Why did I pick this problem? Well, some of you teach kindergarten. Some of you teach college. It would be inappropriate to give you a problem that you couldn't do simply because you didn't remember how to solve a quadratic equation, or you didn't remember what a hyperbola was. It also wouldn't be appropriate to give you a problem that everybody could just get right away and was too easy. So I have a couple of choices. One is to ask you a question about arithmetic that you probably don't know the answer to, like, can you find 5 numbers that do something? Or this, because I think there wasn't anybody in here who felt, oh, I haven't got a chance. I can do this. All of you felt you could do it. And you worked on it, and exactly what I was hoping happened. Most of you thought you had the answer, and then some people got a different answer, and you started talking about it and discussing it, and some learning took place. And we think the answer is 50, right? We think we got to the end of it. Now, what was I trying to teach? Well, I was trying to teach a method of teaching. I wasn't trying to teach a mathematical concept. So that problem is quite different from this one, because in this one, I was really trying to teach my students some mathematics, some important mathematics, some mathematics that actually will go all the way through the year. One of the things I tell them is, look, if you don't know what a line is, there's going to be a problem on the last day of school you're going to get wrong. If you don't know the difference between a line and a line segment, I've got some questions that you're just going to get wrong. But there's more to it. Let's see, this guy. Yes, okay. Why did I pick a 5 by 5? I gave that some serious thought. Why do you think I picked 5 by 5? It's just about complicated enough. Right? 3 by 3 is too easy. 8 by 8, oh, geez. Right? Okay. Now, the next set of questions are probably the most important part, and that is, what else? Are we done? Do we just chuck this away and do it never again? What else can we do with this problem? Well, here's one thing we can do with it. How many are there in that one? Oh, by the way, there's one other thing I forgot here. Couldn't it be that the answer to this one is none? Because you don't know their squares? No. I was very careful to define those as lattice points. And I knew that about a third of you would know what a lattice point is. So I didn't want to get into that. You don't know that there are any squares. Now, he fooled me because I didn't define the problem quite as well. That's okay. But the use of the phrase lattice points is very important because it means that those are right angles and they're equally distributed and all of that. Okay, so what could you do? You certainly could go to a 6 by 6, but what about just going to a 2 by 2? 3 by 3, 4 by 4, 5 by 5. Is there a pattern? Is there a discernible pattern you can see? I was actually playing around with that earlier today, and I discovered something really, really neat. I took Nancy's idea about slope. Nancy, there, okay, she moved. You can't move on me. And I turned it into vectors. And so I said, you know, that this is a 2, 1. So over and up. And how many 2, 1s are there? And I got 4. And when I did that, I noticed 2 really interesting things about how it works out. Some really interesting things about how many you can fit and whatever. So I think I'm ready to do the 6 by 6 and the 7 by 7, and I don't think it's going to be very hard for me to do it at all. Because I took an idea, I took it one step in a different direction, I made a different pattern, a different notation, and the notation led me to another way of thinking about it. But I'm already over time in when do I have to be done? 4 o'clock?
How about 4:04?
Okay, no. Okay, so anyway, there we go. No, okay. Quick, do it. Pardon? What is unique about this simple problem? There is no question. If there's one thing you could change, if there's one thing we could change dramatically about mathematics tomorrow that would improve mathematics education across the board would be to take out the doggone questions. Stop asking those questions. Give them a situation and say, what's a good question? Now, not all the time, but don't you think your kids could come up with 1 or 2 good questions? In fact, I believe they would come up with questions that you and I wouldn't ask. And sometimes those are better questions. And I'll bet you every one of you is thinking of the same question I am. And I'll bet a lot of your kids would too, but I'll bet your kids have other questions too. And I thought of this problem as well during lunch when the guy, this is sort of how the guy was talking about stuff, right? If you drew those little bars, by the way, why are they bars and not line segments? They're not two-dimensional. What's going on with that? I don't understand that at all. Somebody needs to clear me up. There's no two-dimensional aspect, so why are they not just using line segments? I don't get it. Somebody said, well, I know you will, but when you do, don't they get confused because you're using bars? Anyway. Okay.